If you're building a Tesla coil, this is a very important website to go to, www.classictesla.com. This website is maintained by Bart Anderson. He's been doing Tesla coiling for decades, starting with the older spark gap coils and the rotary spark gap coils and the asynchronous and the synchronous spark gap coils. He's responsible for a number of different designs of multi-module capacitors. And he's a great engineer, and he has kept notes of all of his developments over the years, and the sum and total of that is on his website here, Classic Tesla. Highly recommend that you go to it. In fact, I would say that it is an absolutely critical and necessary resource to anybody serious about building coils. End of story. I don't know how you do it without this. Now, a lot of Bart's data comes from his own personal, his own experience, his own trial and error, his own calculations. The foundation of what we're going to use something which I know it's kind of hard to see, but there's a link here called JavaTC, and in fact we're going to go to that. JavaTC is a Java incarnation of a model, of a Tesla coil model, that was developed some decades ago by a group of guys who were researching Tesla coils kind of as a hobby. Now, here's the thing. There's a mathematical model of the coil, the calculus of how the coil behaves under different pulses, and has all been taken care of for you. This is what I'll say about that. There's a lot of theory and a lot of rumor and innuendo and folklore around Tesla coils, that Tesla coils somehow generate energy out of nothing. And I believe a lot of that started because when Tesla did his original experiments, way back at the beginning of the 20th century, a lot was unknown. Remember that when Tesla was doing his work, that radio was unheard of. Radio had just been invented by Marconi. People didn't understand electromagnetic propagation through free space. They didn't understand, Tesla understood it and Marconi understood it, but to most people, radio is magic. So when Tesla comes around and he starts saying, hey, we can generate information by radio waves. What about power? Well, let's just transmit power. In fact, radio waves are power. They're just modulated. And then weak power, and it's modulated, and that's what you pick up. What Tesla was trying to figure out is, wow, can I light a light bulb from far away, transmitting power through the air? And the answer is you can. You totally can, but it's really inefficient. And in fact, had he lived longer, he did, he probably eventually figured out that it wasn't an efficient way to transmit power. Now, back when he published his papers, all this stuff was new and exciting, and to the average person, and even the average engineer, there may have looked like there was some magic involved. So that's, I think, where when you read these papers and everything sounds fishy and strange and like like there's some kind of paranormal forces going on, or maybe zero-point energy, or whatever people want to say. It's because back in the old days they didn't know about this stuff, and they couldn't tell whether it was paranormal or normal. Now here it is 100 years later, and we know what the physics is behind this. There's nothing mysterious about it. It's an air core. It's an air core transformer, and it's two coupled LC circuits. The reason there's not a whole lot of science behind it is it's not particularly useful for anything. It's fun to generate the sparks, but it's not particularly useful in electronics. If it was useful, you'd see it all over the place. We use wires to conduct our power because it's just much more efficient. We use radio antennas to transmit radio waves because it's just much better, and we're using low power. A Tesla coil turned out to be not so good for anything. And it does transmit power over very short distances, but it's very, very inefficient. So there hasn't been a whole lot of work done in this over the years. And then back in the 90s, 80s and 90s, a bunch of guys who worked at various places, Lawrence Berkeley Labs and Fermi Lab, and a bunch of scientists and engineers got together and said, hey, let's actually finish, continue where Tesla left off and model this thing, create mathematical models of the coil, so that we can do calculations and figure out what the voltages are and how to figure out the frequencies and whatnot. And so they actually, using modern math, did calculations and created a model for the secondary and the primary interactions on a Tesla coil. If you've got a mathematical model, then you can put it onto a computer. And that's what happened. So they did a math model. I think they originally did their calculations in C. Over the years, C++ came out, Java came out, and Bart Anderson took their papers, read the engineering papers that they published, took all that math and put it into a format we can use. So now, without having to know the physics or the math, we can use those calculations to figure out how to make a useful Tesla coil. It still seems somewhat dense. And the truth of the matter is, the fact that it seems dense doesn't mean that it is. Again, there's no paranormal effects, there's no zero-point energy, there's no energy coming from nothing, there's just regular old math and electronics. And the reason it seems mysterious is that people stopped working on it years ago because it didn't do what Tesla really wanted, which was transmit usable power without wires through space. You can transmit the power, but it's very inefficient. We benefit because, as hobbyists, we've got these guys who are a lot smarter than us who created this math model. Anyway, let's figure out how to use JavaTC here. Enough of that lecture. So if I move in here, we're going to see a number of things on the top row. So what we're going to try to do is, I'm going to take the measurements that I made before, and I'm going to plug them into JavaTC. Now, I know what the right answer is here. I know that I need to have my center frequency around between 30 and 70 kilohertz, because that's what the transistors that I'm using resonate at best. The lower the frequency, the better. In fact, closer to 30 I can get, the better. I know that when I tapped, my primary tap point for this coil is around 4 turns. If I don't get an answer that tells me 4 turns and somewhere between 30 and 70 kilohertz, then I'll know that I took the measurements wrong. So I'm going to try to reverse engineer what I did for that coil. So let's enter some of this data. Okay, so I know that my primary capacitor is 3 strings of 10 2 microfarad capacitors. Now another thing I'm going to do is I'm going to take you to a different website. Hang on a sec. All right, I'm going to take you to a website called deepfriedneon.com. I just like the fact that they've got a capacitor calculator in here. You can find these all over the place, but there's a nice capacitor calculator in here that I'm going to use. So I'm going to go to this Tesla coil design guide. Oh, that's not what I want, actually. I want to go to equations and data lists. I want to go over here to MMC calculation, and I'm going to use this to give me a final capacitance. Now let's see that I'm going to plug into JavaTC. So each capacitor that I'm using is an Ariovox 2 microfarad, 2.0 microfarad capacitor. I know that the voltage rating on each one of them is 1,000 volts. I know that I've created a string of 10. I've got 10 capacitors per string, and I've got 3 strings in parallel. Therefore, the total capacitance of 3 strings of 10 in parallel is 0.6 microfarads. That's what I said before. That particular module of capacitors is capable of withstanding 10,000 volts before it fails. If you want to derate that like a good engineer, you'll cut that in half. So let's say 5,000 volts before it fails. We're not even going to come close to 5,000 volts with what we're doing. And we need 30 capacitors. That's what this tells us. So if I go back to JavaTC, I know what I'm going to enter here for my primary capacitor is going to be 0.6. Now, if you didn't know that, and you can play around with these numbers, you'd pick something, close to what you think, and you have to try. But I know that I'm going to start with 0.6 because that's what's in that coil. And you could use these numbers, all the numbers I'm typing in, you can use it as a sample coil. Now, the other thing you can do here is Bart himself has got a sample coil, and you can bring that up, click this, bring up the sample coil, and you can play with those numbers and build something that's like his sample coil. His sample coil works, so you could do that if you want. I've got a sample coil, which is my actual coil. It's in my garage. So let's continue here. So ambient temperature, 68 degrees. I'm not sure that really matters so much. That's 68 Fahrenheit. Doesn't really make any difference to me because I'm going to only run this, when it's kind of warm outside. The temperature will matter. It'll affect the length of the sparks, but it's not so critical. I'm going to leave that at 68. I'm going to do my units are inches. My secondary wire material is copper. You saw that 26 gauge copper wire. Primary is copper. It's 1/4 inch tubing. The primary wire is round 1/4 inch tubing, and so that's the first line here. Now, insert value for the ground plane and if the coil is inside an enclosed space. Well, the ground plane for the coil for what we're doing here is basically the earth, the ground itself. We're not creating an artificial ground. We could imagine putting this coil on a tabletop if it was small enough and putting it on a giant metal plate and grounding the plate. We're not going to do this. This coil, the ground plane, is the earth itself. So I'm going to leave all these things blank because I'm not creating an artificial ground. The ground plane is at 0 inches. By default, the ground is at 0 inches. That's where it is, and I'm going to leave that. Now let's insert the values for the secondary coil. One thing to note, if I didn't know what any of this meant, I could actually click here. Bart's got links to some of the definitions. So let's see, if we zoom out, you can see it'll tell you what these things mean. I'm not going to go through that verbally. You can look at that yourself. So I'm going to go back to JavaTC and zoom back in on what I was doing. Hopefully this thing will focus. There we go. All right, so values for the secondary coil. Now, here's what I know. The radius of that, the outer diameter, the radius of that tube, right, was about 4. I'm going to clear this over here. I'm going to bring a calculator in here. Here we go. All right, so I know that the OD of that tube was about 8.78 inches. Excuse me, 8.78. That's wrong. So it'd be 8.875 inches. I'm going to divide that by 2 to get the radius, and I've got basically 4 7/16. So this is 4.4375. So that's what I'm going to put here. The radius 1 is the radius at the top of the secondary. Radius 2 is the radius at the bottom of the secondary. This is a cylinder, so the radius is continuous all the way down. You might want to create a cool-looking Tesla coil that had the secondary as a conical shape or some other weird shape. I mean, so if you're experimenting with those things, you can do that. People have made really cool-looking coils that way. In our case, the radius at the beginning and the end, at the top and the bottom, are exactly the same, and that number is 4.4375. 5 on the top and 4.4375 on the bottom. Now, what is the height of the radius, of the secondary rather? Well, in this case, I'm going to say the secondary is above the ground. It's on a stand that I made, and I'm going to say roughly that it's I don't know, it almost doesn't matter, but I'm going to say it's 2 feet above the ground. Maybe it's 2.5, maybe it's 3 feet above the ground. So I'm going to say it's 36 inches off the ground. That's the height of the first turn of the secondary above the surface of my garage floor, right? It's 36 inches above the ground. Now I know that the number of turns, the height of the number of turns, I had about 36 inches worth of turns on the secondary coil. So if it's 36 inches above the ground and the length of the turns of the coils themselves are 36 inches. 36 and 36 is 72. So the bottom of the first turn is 36 inches above the ground. The very last turn is 36 inches above that. In fact, maybe that's confusing. Let me put round numbers in here. Let me just say, for the hell of it, that the bottom is at 30 inches. And the top is 36 inches above that. So that would be 66 inches. All right. Now, how many turns do we have? I've measured this myself, and I know there's about 2,000 turns, but suppose I didn't know that. Okay, I can come to this screen over here. So let's go back, and this screen over here will give me a rough calculation of how many turns that I've got. So we know that the radius is 4.4375, both for the top and the bottom, 4.4375. For the sake of this calculation, I'm going to say the height above the ground plane is 0. It really doesn't matter. I'm just trying to calculate how many turns I have. And the last turn at the very top is 36 inches. Now, bare wire diameter. If I come down here, let's see, let's go out a little bit. If I click this guy over here, I get a nice pull down that will give me, for the wire gauge, what the different sizes are. So I know I'm using 26 gauge wire. So let me zoom in again. So I'm using 26 gauge wire, and that tells me the bare wire diameter on 26 gauge wire is about 15,000, 16 thousandths. So I'll enter that in here, 0.0159. You know, just for the sake of argument, I can say 1/6. I mean, insulation thickness is looking like, this is single thickness insulation, is looking like 0.0011. And spacing between turns, if I'm lucky, is 0. That means that I've compacted this. I didn't leave any space between the turns and the secondary. So if I calculate, what that's telling me is I've got 1,978.2 turns. That's close enough for government work. It's about 2,000, and that more or less goes with what I measured with my ruler. So if I come back over here, I can say 1978 turns, and over here I can say that American wire gauge is 26 gauge for the wire. Okay, so that's that. Now let's go for the primary. This is going to be slightly more complicated. So the primary, the radius of the primary, if we remember, the first turn of the primary, the inner edge of the primary, was at 1 3/4 of an inch. Let me get rid of that. It's this over here. Let me go back to my calculator. Where is it? Come back, calculator. Okay, there you are. All right, let's clear that. So I know I had 1 3/4 inch to the inner edge of the primary, and I've got to add to that the radius of the secondary itself, which was 4.4375. All right, now I guess if I was really picky, I would add to that or subtract from that the thickness of the wire itself, but I'm not sure that's going to make too much of a difference. Anyway, I'm going to enter this 6.1875 is the inside radius of the primary. So 6.1875. Now, the outside radius, that's an interesting proposition. Here's what I know. I know that I have 1/4 inch tubing, and I know that it's a spiral tube, and the spiral, each turn of the spiral is a 1/4 inch from the previous one. So if I take a 1/4 inch plus a 1/4 inch, I get a 1/2 inch. So every turn is a 1/2 inch. If I measure the center of the tubing, each turn is a 1/2 inch away from the next turn. So at this point, in theory, I don't know how many turns I got. I can pretend I don't know how many turns I got. Let's say I got 10 turns. If I have 10 turns, that means that the overall width of my overall radius is going to be 5 inches. 10 times a 1/2 inch. It's going to be 5 inches apart. I mean, from the beginning to the end. So again, I'm using 1/4 inch coil. I'm spacing the 1/4 inch refrigeration tubing. I'm spacing each turn a 1/4 inch apart. So 1/4 inch plus a 1/4 inch is a 1/2 inch, And I'm going to say I have 10 turns. So 10 turns measured from the center, measured from anywhere actually, is going to be 5 inches in radius. So 5 inches plus 6.1875 is going to give me 11.1875. And that's going to be my outer radius. Now the height. As we remember, I made the top surface of the primary about an inch below the first turn of the secondary. If we look up here, the secondary, the first turn is at 30 inches above the ground. And so the primary is an inch below that. I'm going to say that's at 29 inches. All right. And in fact, the last turn of the spiral, because it's a flat spiral, is also at 29 inches. I'm going to say that I did 10 turns. Now, again, that's hypothetical. We know that I don't have 10 turns, but I need to put something in here. And the wire diameter is a 1/4 inch, 0.25, 1/4 inch. Okay, so I've now entered that. Now, we've got to talk about the toroid itself. The toroid minor diameter I measured was 6 inches. The major diameter is 24 inches. And the way this works is I know it's a top load, and the center height, as you remember, I put it about 1.5 inches above the top turn of the secondary. So the top turn of the secondary is at 66 inches. This is 66 right here. So 1.5 inches above 66 is going to be 67.5. 67.5 inches. I'm going to add that. What this lets you do is you can add a number of different toroids. You can put spheres. I mean, again, this is for an experimenter who's trying different things for his coil. So if we go down here and take a look, here's a little model that, let's get that on screen. Here's a little model that JavaTC is creating for me at the moment. This is sort of what it thinks my coil looks like, and in fact, it sort of does. Here's the top load, and here's a side view of what the primary looks like. Here's the secondary sitting right there. So that looks pretty close, right? So what I'm going to say to JavaTC, now I'm going to run this. I'm going to run an auto tune and say, okay, I'm not sure I've tuned it correctly. I've put 10 turns, but you figure out if that's right. I'm going to leave the coupling the way it is. I would sort of like it to adjust the coupling, the K, to what it thinks it should be. Let's see what happens. All right, so I'm going to run JavaTC, and I press it and I run it, and I get a bunch of numbers out here. Now, first thing I notice is that it's telling me my resonant frequency is 68.18 kilohertz. Now, again, I know this coil works. That's pretty close to 70 kilohertz. That's, you know, kind of high for the transistors that I'm using, but I know it works, and it's lower than 70, so it's kind of a first cut gut reaction. I'm feeling kind of okay about that. Now let's take a look at the coupling coefficient. Coupling coefficient, I recommend it is 0.144. All right, it's telling me my K should be 1.144. What I've really got is 0.123. And that's okay. My K is lower than the recommended. That means I could probably raise the primary a little bit and increase the power transfer. But, you know, again, I know this coil works. So I'm okay that my K is lower than the recommended coupling coefficient. So I'm feeling good about that too. Now let's go check what it thinks my primary turn should be. Okay, this is interesting. So it's telling me that I should have let's put that closer to the center of the screen. It's telling me that I should have 3.7 turns on my primary. Well, as you remember, we were at like 3.9, 3.8 turns in the primary, so we're pretty close to what JavaTC says I should have. So I'm feeling good about these numbers. Some other things it's telling me, I mean, it's just kind of interesting. The overall DC resistance of my primary is 2.29 ohms. I guess if I took the ohm meter out, I can go measure that. The length of the total tubing that I'm using is 13 feet. It's telling me that the capacitance size, it thinks I should probably use 0.599956. That's close enough to 6 microfarads. It's telling me what my mutual inductance is, total energy transfer time. This is all interesting stuff. Now, again, I know the coil works, so if I really wanted to double check, I could go back and measure these things. I could measure the resistance of my secondary and whatnot. All these numbers are pretty useful. But the main thing is here that when I go back and reposition this coil on a new base, I know that if I use the exact same materials, 1/4 inch tubing for the primary, if I use the same capacitor and whatnot, I can expect 3.7 turns for the tuning for the primary. I can expect that at resonance I've got 68 kilohertz. I mean, I really like that to be lower, but to lower it, I'd have to put more turns on the secondary, and I can't do that. It's already built. So, generally I'm okay with this. Now, other things that JavaTC does, it's got power calculations, and this, as he says, it's not for a DR SSTC. If you're doing a static gap coil, you can enter in your transformer parameters in here. If you've got a rotary gap, you can enter it there, and it'll give you some really nice power transfer numbers. We're not using that. And that brings up one last thing I'm gonna say. For a DR coil, you actually want a bit of detuning between the primary and secondary circuit. And here it says we've got no detuning. This thing is, the primary and secondary are tuned exactly alike. You'll remember that my primary, I was looking at close to 4 turns, not 3.7. Now, one reason this may work well is because I've actually detuned it, and that detuning is something that's necessary for the pulse correction for the driver transistors themselves. So that may be one reason this works great. This says if I have 0% detuning, I'd need 3.7 turns. I'm using 4, so I'm detuned probably exactly enough. I think we want, I'll have to go back and look, but I think we want about 10% or 15% detuning. So if it was 10% of this, that would be roughly 4 turn, 0.4 turns, which would be kind of what we see. So, okay, so that's how I ran JavaTC. You can run the same thing, and all right, that's that part of the discussion. One last thing I want to point out here. So when I'm rebuilding the coil, I'm going to swap out the primary. Instead of using 1/4 inch refrigeration tubing, I happen to have a really nice coil of 3/8 inch refrigeration tubing. So, the difference between the 3/8 and the 1/4 is an eighth. So it's going to change the values for the primary just a little bit here. So as you can see, the wire diameter that I've got here is now going to be 0.375 3/8. I'm going to start it at exactly the same spot, but the distance between each turn is going to be basically 3/8 plus 1/4, which is going to be 5/8. And so when I enter all that in there, what it's telling me is that the number of turns that I can expect to tune this is going to be basically 3.8. So it's not going to change the frequency of anything any, but what it's going to do is change the geometry a bit. So I'm going to tune at roughly the same spot, but the outer edge is going to be 9 inches, well, 8.5 instead of a shorter distance, because I got 4 turns at 3/8 instead of 4 turns at 4 turns at 5/8 spacing rather than 4 turns at 1/2 spacing. So it's a small difference, but I wanted to check it on JavaTC. So what's going to happen is when I go down to the model here, my primary is going to be a little bit wider. It's going to change the K a little bit. It's going to bring the K up very slightly. So that's not going to change too much. It's going to change the radius of the primary, but generally my tuning point is going to be in roughly the same spot. So that's what I'm going to do. I'm going to use the same secondary. I'm going to use different primary tubing, 3/8 instead of 1/4. I'm going to tune it at roughly the same spot. I'm going to make the height of the top of the coil roughly at the same spot. The height of the primary and the secondary roughly the same distance apart, an inch and a half. And I'm not going to change where the top load is, same top load. So that gives me some confidence that I can pretty much build the primary the same way I built it. Only I can use 3/8 inch coil, and I'll just keep it at 1/4 inch separation. Okay, so that's enough for this this video. Hope it was somewhat instructive. Hope you go to Bart's site and try out JavaTC. If you got any questions about it, I'd be happy to answer what I can. You can see that a lot of complicated math is done for you automatically by this great program. It's free. Thanks to Bart Anderson for putting it together and making it available to all of us. Okay, thank you very much. See you later.